Okay, we are going to look at the number e, hence the big E in this video here. I'm actually going to let somebody else explain this a little bit. So there's a YouTube channel called Numberphile. File means like or love. So if you are a cinephile, cinema, you love the cinema. If you are, I don't know what book file would be, but if you love something. So Numberphile, all about numbers. Philosophile, you love philosophy. So that's the idea. I'm going to let him explain it a little bit. I'm going to skip around to more of the complex math, binomial theorem, stuff like that we're not going to worry about. This number e is really important. It shows up in this chapter. It's going to show up in a couple of the different sections. And so this guy here, he's going to explain it to you a little bit.
We're going to talk about e, the big famous constant e. Okay, it's one of the famous mathematical constants, one of the most important. It goes along with pi and, I don't know, golden ratio and square root of 2. There are constants in maths that are the most important constants. And e is one of those constants. So e is an irrational number, and it's equal to 2.718281828 something. The problem with e is it's not defined by geometry. Now, pi is something that's defined by geometry, right? It's the ratio of a circle circumference and its diameter, and it's something the ancient Greeks knew about. And a lot of mathematical constants go back to the ancient Greeks, but e is different. E is not based on a shape. It's not based on geometry. It's a mathematical constant that is related to growth and rate of change. But why is it related to growth and rate of change? So let's look at the original problem where e was first used. So we're going to go back to the 17th century, and this is Jacob Bernoulli, and he was interested in compound interest, so earning interest on your money. So imagine you've got £1 in the bank. You have a very generous bank, and they're going to offer you 100% interest every year. Wow, thanks a lot, bank. So 100% interest, so it means after 1 year, you'll have £2. So you've earned £1 interest, and you've got your original pound. So you now have £2. What if I offered you instead 50% interest every 6 months? Now, is that better or worse? Well, let's think about it. Okay, you're starting with £1, and then I'm going to offer you 50% interest every 6 months. So after 6 months, you now have £1.50. And then you wait another 6 months, and you're earning 50% interest on your total, which is another 75p. Then you add on to what you had, so it's £2.25. Better. It's better. So what happens if I do this more regularly? What if I do it every month? I offer you 1/12 interest every month. Is that better? So let's think about that. So after the first month, it's going to be multiplied by this. 1 plus 1/12.
You should start to recognize this formula a little bit because we already talked about compound interest.
So you do that, that's your first month. Then for your second month, you take that and multiply it again by the same value. And your third month, you multiply it again and again. You actually do that 12 times in a year. So in a year, you would raise that to the power 12, and you would get £2.61. So it's actually better. In fact, the more frequent your interest is, the better the results. Let's start with every week. Okay, so if we do it for every week, how much better is that? Okay, what I'm saying is you're earning 1/52 interest every week. And then after the end of the year, you've got 52 weeks, and you would have £2.69. So it's getting better and better and better. In general, you might be able to see a pattern happening here. In general, it would look like this. You've been multiplying by 1 plus 1/n to the power n. Hopefully you can see that pattern happening. So here, n is equal to 12. You do it every month. 52, you do it every week. You did it every day. It would be £1 multiplied by 1/365 to the power 365. And that's equal to £2.71. Right, and so it would get better if you did it every second or every nanosecond. What if I could do it continuously? Every instant, I'm earning interest, continuous interest. What does that look like? That means if I take this formula here, 1 plus 1/n to the n, I'm going to n 10 to infinity. That would be continuous interest. Now, what is that? What is that value? That's what Bernoulli wanted to know. He didn't work it out. He knew it was between 2 and 3. So 50 years later, Euler worked it out. Euler, he works everything out.
Anyone else?
Yeah, it's either Euler.
Yes, Gauss and Euler are really big names in mathematics.
4, 5, 9, and so on. You're right. We're getting closer, weren't we? We're getting closer and closer to this value. So already we're quite close to it. If you did it forever, though, of course, you would have this irrational number. Now, Euler called this E. He didn't name it after himself, although it is now known as the Euler constant.
Why do you call it E then?
It was just a letter. You know, he might have used A, B, C, D already for something else, right? So you use the next one. It's a lovely coincidence. I fully believe that he's not being a jerk here, naming it after himself, but it's a lovely coincidence that it's E for Euler's number.
Would you have called it G if you discovered it?
I would not have called it G. No, I would have hoped somebody else would have called it G, and then I would have accepted that. Euler proved that this was irrational.
We're going to skip over the proof of that. You are more than welcome to search this on the internet and find it yourself. We're going to jump to this spot here.
Okay, why is E a big deal? It's because E is the natural language of growth. And I'll show you why. Okay, let's draw a graph. Y equals e to the x. So we're taking the powers of E. So here at 0, this would cross at 1. So if you took a point on this graph, right, the value at that point is e to the power of x. And this is why it's important. The
gradient is like the slope.
The gradient of the curve at that point is e to the x. And the area under the curve, which means the area under the curve all the way down to minus infinity, is e to the x. And it's the only function that has that property. So it has the same value, gradient, and area at every point along the line. So at 1, the value is e to the power 1. The value is 2.718, the gradient is 2.718, and the area under the curve is 2.718. The reason this is important then, because it's unique in having this property as well, becomes the natural language of calculus. Calculus is the maths of rate of change and growth and areas, maths like that. And if you're interested in those things,
So if you're continuing on your math to calculus,
then the maths becomes much simpler. Because if you don't write it in terms of E, you get lots of nasty constants. And the maths is really messy. If you're trying to deliberately avoid using E, you're making it hard for yourself. It's the natural language of growth. And of course, E is famous for bringing together all the famous mathematical constants with this formula, Euler's formula, which is e to the I pi plus 1 equals 0. So there we have all the big mathematical constants in one formula brought together. We've got e, we've got I, square root of minus 1, and we've got pi, of course, we've got 1 and 0, and they bring them all together in one formula, which is often voted as the most beautiful formula in mathematics. I've seen it so often now, but I'm going to change it to it. Don't put that in the video.
all right, so we're going to stop there with the video. Again, number file, great video. There's lessons. It's random stuff like, oh, the probability of flipping heads when you're for the Super Bowl, or again, very random things. Check it out if you have any interest in why some people are so excited about numbers and so excited about math. They do a great job of showcasing some of the more random things in math. But getting back to our unit here, E, this number E, is used for continuous growth. So one place that you're going to see it, I don't want to play that, no. There we go. One place you're going to see it is when we look at this compound interest. He alluded to that as being kind of the original part of this problem. This was our compound interest formula. If you have continuous compound interest, it looks like this. So just a slight difference in how we write it. There's no compounding, so there's no n to compound with. It's the principal, the amount you invested or borrowed, times e to the power of the rate, again as a decimal, not a percent, times the time. This is also going to come up when we talk about population growth, because population growth is not compounded. You don't have new births and new deaths every quarter. It's instantaneous. It just happens all the time. And so this instantaneous growth and decay involves this number e, and this formula is going to pop up in a couple different places where there's continuous things happening. So I'm going to stop there with this video on e, and we'll move on to something else in the next video.